Our presenter today is Carlos Valenzuela Morales. He's a senior applications engineer here at Orolia, formerly of Seven Solutions, a company we partnered with for years and had the fortune of acquiring late last year. Carlos holds a master's degree in telecom engineering and specializes in the design of resilient PNT timing solutions based on White Rabbit, which uses PTP to achieve sub-nanosecond accuracy. And he's got some great work to share with you on just that topic as it relates to radar applications. So with that introduction, Carlos, take it away.
Great. Thank you very much, Eric, for the introduction. So I think we can just get started. So this is the agenda we'll cover in this presentation. We'll start providing the context of the scenario and applications we are discussing within the defense sector and the challenges in terms of synchronization which are associated to them. Then we'll focus already on the radar systems, providing some background on its evolution and the synchronization requirements related to each type of radar system we are considering. At this point, once we have already presented the challenge, we will focus on the solution we propose for this scenario. For this, we'll start by presenting the solution ecosystem, including the different products and technologies involved. As we'll see, our technical solution is based on White Rabbit synchronization protocol, so we'll also present the basics of this technology. And finally, the most important part of the presentation will be explaining 3 different use cases related to the 3 types of radar system we'll focus on. These are the monostatic radar, the multistatic radar, and the phase array antenna or IEEE. As we'll see, the last 2 will be the most interesting ones from the synchronization perspective. After this, we'll just finish the presentation with the conclusions, and as Eric said, we'll have a Q&A session. So our context is the C5 ISR, which is basically the system of systems that allow the entire military mission to successfully operate. To achieve this, the system must allow the transmission and storage of real-time information to ensure an accurate situational awareness on the battlefield, which will enable the capability of making the correct decisions on it. The system of systems consists, as we can see in the figure, on multiple platforms and multi-domain operation, which include distributed systems of sensors, radars, command and control centers, GNSS receivers, etc. The requirement of the C5 ISR are achievable by implementing a network capable of connecting all these elements and enabling the exchange of synchronized data over reliable low-latency links. So we are talking about a network based on a high number of elements connected in mesh topologies, typically, which will require high-performance timing, distribution, and resiliency in order to operate correctly. Plus, the C5 ISR requirements are becoming more exigent. It seems there is some problem with the, I see in the questions. I don't know if they are visible, the slides, or it's only the audio.
The slide should be visible for anybody. If anybody else is having an issue, please just post in the questions to the person who asked. I think if you refresh your browser, you might be able to see them.
Okay, great. So for now, let's continue. If there is any problem, please let us know. Okay, so as I was saying, the requirements of the C5 ISR are becoming more exigent to meet the evolving adversary capabilities, which leads to even more demanding synchronization requirements. In this presentation, we'll focus on the synchronization requirements for the radar systems as the key element of this network, but it is important to remark that very similar requirements apply to other distributed elements of the system. In this slide, we mention some of the top challenges which must be addressed while implementing the mentioned network. First of all, the need of providing high-performance synchronization in mesh networks to multi-platform equipment, which can be located in wide area scenario. This includes providing a very stable frequency signals with low phase noise, for example, for the radars, oscillators, and up and down converters, also very accurate time signals for event triggering, time stamping, data processing, etc., and interoperability with multiple timing interfaces and protocols for synchronizing different platforms. It will be also very important ensuring the system scalability for the exponential growing complexity of these systems. This must be done, of course, optimizing the costs. And finally, we have the need of providing resiliency. So here we are talking about protection against failures and attacks connected with the electronic warfare, which includes interference, jamming, and spoofing. We also consider cybersecurity and monitoring capabilities for controlling the status of the network. We'll now focus on the radar systems. As an introduction, we present in this slide a very brief summary of the evolution of the radar systems. With this, we intend to show how the systems have grown in terms of capabilities, but also complexity, which leads into new challenges and requirements related to synchronization. We start on the left with the monostatic radar, which is the conventional radar system. In this case, the radar either uses the same antenna for both the transmitter and receiver elements, or they are collocated. This type of radar system relies on the use of very stable local oscillator for synchronization purposes. So in this case, the implementation of the timing solution is quite straightforward and consists basically on providing locally the frequency and time signals to the different elements of the radar. The real challenge will appear when the system is distributed, which is the case of the next type of systems we are considering as part of the evolution. For example, we have the multistatic radar, which is a system based on multiple monostatic and bistatic components. So having bistatic components means that the transmitter and receiver are in separate locations. So basically, as we can see in the figure, we can have an scenario with multiple transmitter and receiver elements covering a wide area. These radar systems provide multiple advantages, such as increasing the coverage of the surveillance area, increasing the possibilities of detection, and facilitating the countermeasures against attacks. For example, it will be less vulnerable to jamming. But on the other hand, it also introduces the requirement that all the locations must be synchronized to the same time reference for the radar system to have optimal performance. So this is providing reliable information about the position and velocity of the target. Finally, we have the phase array antenna, or AISA. In this type of radar, multiple radiation elements are fed with a specific phase shift in order to control the beam steering electronically. So this allows the multifunction operation of the radar by generating simultaneously multiple STIMs. And it also provides fast change of the beam direction and agility. So a single radar system can be used for surface and air detection and tracking. The synchronization challenge in this case will be providing the necessary time and frequency signals to a high number of radiation elements, maintaining, of course, the high performance. Also, and as the last step of the evolution, we consider the possibility of integrating the phase array antenna in the system of systems, as we can see in the figure. So at this point, we have already presented the problem, and now we will focus on the solution. For this, we present in this slide the product's ecosystem, which can be used to implement the synchronization solution for the radar systems that we mentioned. We are considering from left to right 3 different layers of the network architecture. In the left side, we have the time servers. These devices will provide the time reference based, for example, on its integrated GNSS receiver. So we show here the Secure Sync 2400 and the VersaSync, which is a ruggedized form factor. These devices will be the master clock of the network, providing the primary time reference and also multi-layer resilient capability to protect against the GNSS vulnerabilities. This capability includes anti-jamming antennas, the use of multi-constellation and GNSS protected signals. So this is at the GNSS receiver level, and then the interference detection software and the capability of using multi-source time references. So once an attack or interference is detected on the GNSS, the system will automatically switch to the next time reference available, which can be network-based, or like PTP or NTP, local signals, other satellite solutions such as STL, or an internal holover clock. In the center of the slide, we have the White Rabbit Z16, which is the fan-out device for distributing the timing over the network by using the White Rabbit protocol. We'll see in the next slide what is exactly this. And finally, on the right side, we have the White Rabbit end nodes, which will receive the White Rabbit feed from the distribution network and provide the interface with the radar equipment. As we can see, there are multiple form factors that can be used depending on the timing interfaces required on the end nodes and also the integrability requirements. As we can see, there are boxes such as the White Rabbit Zen with 1U and 2U form factors, the White Rabbit LEN, which has a compact size form factor, but we also have timing boards and IP cores, which must facilitate the integration of the White Rabbit synchronization capability in the radar equipment. As I mentioned, White Rabbit is the technology we use for the accurate timing distribution. White Rabbit is basically an implementation of the PTP synchronization protocol designed to achieve sub-nanosecond accuracy in Ethernet-based networks. It is also the basis of the high accuracy profile of the new PTP standard, which is the IEEE 1588-2019. In this slide, we see some of the main features of the technology and the reasons why it will be very suitable alternative for the applications we are discussing. We'll go into further details later, but some of these features are, of course, the high accuracy, which, as I said, is sub-nanosecond level. In fact, we can see in this figure how the White Rabbit improves the synchronization precision and stability in comparison with the default version of PTP. But also it has other relevant features as the scalability and the possibility of easy deployment, avoiding complex calibration procedures. So now we'll present the solution we propose for each type of radar system that we have mentioned previously by using the product ecosystem that we have also presented. So we start with the monostatic radar, which is the simplest one. At the top right corner, we have a figure which specifies the main elements of the monostatic radar. In the right side of the antenna, we have the transmission elements, which are the signal generator, the RF up convert, which is used to convert the signal from baseband to high frequency, and the power amplifier. On the left side, we have the receiver side with analogous elements. As we can see, the same clock reference is necessary to be provided for both transmitter and receiver side. And for monostatic radar, this is typically done by using a very stable local oscillator. So for implementing this solution, it is possible to use a secure sync, which will provide all the necessary timing signals using GNSS as reference. The fact of using GNSS reference will ensure the long-term stability. This way, we can avoid relying on local oscillator working in free running, which are influenced by aging, temperature variations, and other environmental factors. The solution will be resilient against the GNSS vulnerabilities due to the multi-layer protection that we described previously. Plus, the secure sync with, for example, rubidium configuration will provide the frequency outputs with low phase noise required for the radar, as it is necessary to obtain accurate information on the target velocity. For example, for Doppler measurement, where noisy signals may mask the detection for slowly moving targets. And finally, the secure sync can also provide different time signals such as 1 PPS, IRIC-B, etc., which can be used for time stamping and data processing. We present now the solution for the multistatic radar. In this scenario, the White Rabbit technology is a very suitable alternative to meet the timing requirements by distributing the necessary frequency and time signals to each radar element, which will be in separate locations. First of all, the fact of using Ethernet-based protocol for timing distribution will help by reducing the costs related to the deployment and maintenance. For example, the existing optical fiber infrastructure can be used for transmitting the timing along with the data over the same network. Then, the timing performance of White Rabbit protocol will allow to meet the most demanding synchronization requirements and improve the performance of the radar system. So we'll be able to transfer the time with sub-nanosecond accuracy and picosecond level jitter for improving the time tagging for data fusion. The phase information is also very relevant for applications such as interferometry, time impulse transmission, and range estimation. As an example, a time error of 30 nanoseconds between the transmitter and the receiver, which is a typical error in the GNSS-based systems, will mean that the range measurement includes an additional 30 nanoseconds, which will translate into detecting the target 10 meters away from its actual position. At the same time, the system will provide low phase noise clock signals for improving the signal acquisition and tracking processes. Another important point is the capability of synchronizing GNSS-denied scenarios, as no GNSS reference will be required in the different sites for synchronization purpose. In addition, the White Rabbit solution will provide great scalability, as the timing performance will not be impacted by factors such as the network traffic, the number of nodes of the system, or the length of the links. Finally, the solution also includes network resiliency in the distribution network. At this layer of the network architecture, based on the use of multiple time sources and the failover and monitoring mechanisms. So in this diagram, we can see an example of a possible solution which can be implemented for this application. In the top of the network topology, we'll always have the time server, Secure Sync 2400 in this case. Then a first White Rabbit Z16 node working as a White Rabbit Grandmaster will retrieve the time reference and distribute it to the different locations following a tree topology. So in this case, we are considering two sublayers in the distribution network. As end nodes, we have White Rabbit Send TPFL devices, which provide the 1 PPS, 1 pulse per second, and clock signals to the radar element, which is located on each site. We also consider the possibility of providing the time reference used for our multistatic radar to other systems of the network by using White Rabbit links. Now we'll analyze the case of the phased array antenna. In this case, the radar system is based on a high number of radiating elements which must be synchronized with high accuracy. Again, we'll have to provide time signals such as 1 PPS, ensuring sub-nanosecond accuracy in all the nodes, and also frequency signals, typically 10 MHz, with very low phase noise. So in this case, we are using a VersaSync as time server, as a ruggedized form factor will be convenient for this scenario. We have already mentioned the scalability of White Rabbit. Thanks to this, we'll have the flexibility for implementing different topologies in order to optimize the design of the timing solution. So in this figure, we have an example of a possible solution for synchronizing subsystems of more than 100 elements. So we can see that a single White Rabbit Z16 is distributing timing to each subsystem, which is implemented by a matrix of White Rabbit nodes connected in daisy chain topology to each port of the White Rabbit Z16. Each White Rabbit node of the matrix provides frequency and time signals to the radar elements. And thanks to the White Rabbit characteristics, we can ensure that the performance, even in the last nodes of the daisy chain, will be still compliant with the synchronization requirements. Another interesting feature of the solution is the capability of providing programmable phase and frequency outputs. So for example, the White Rabbit set family products integrate the capability of shifting the phase signals with picosecond precision. This could be useful for implementing the beam steering. So it is possible changing the angle of the radiation pattern in the phase array, without using any additional hardware. Another important requirement in this application is normally related with the integration of the timing solution in the radar infrastructure. So normally there will be restrictions in the dimension of the form factor, also related to power supply, cabling, etc. And in order to facilitate this integration, we order different alternatives. So for example, the White Rabbit nodes that we can see in the diagram can be based on OEM modules or timing boards with reduced dimensions, or even we can integrate our White Rabbit IP core in third-party FPGA nodes to make them White Rabbit compliant, so they can receive directly the White Rabbit feed in the radar equipment. So we have already mentioned the performance that it's possible to achieve with the White Rabbit solution for the cases of multistatic radar and phased array antenna. But now we'll show the specific test results we obtained in the lab using the setup that we can see in this figure. So this setup represents a simplified network topology based on the network architecture which implements the solutions we presented before. Using this topology, we'll be able to see how the system performs in a scenario with multiple hops and also long-distance links. So basically, we have a secure sync as a time server and a White Rabbit Z16 as a White Rabbit Grandmaster device, which connects downstream with a daisy chain based on 10 White Rabbit CentiPFL nodes. In this test, we measure both the time and frequency performance. So for the time, we use the 1 PPS outputs to calculate the time error on each node with respect to the Grandmaster. And for the frequency, we calculate the phase noise performance of each node by comparing its 10 MHz output with the reference. So these are the results we obtained for the time transfer performance of the system. We can see in this table a summary of some relevant statistic parameters such as the synchronization accuracy, peak-to-peak error, and jitter. So we can see how the accuracy is maintained below 500 picoseconds in the daisy chain. The peak-to-peak error is also sub-nanosecond, showing values below 700 picoseconds even in the last node of the daisy chain. In the jitter, we see that we obtain around 15 picoseconds in the first nodes, but even in the last one, the jitter does not go higher than 90 picoseconds. So this is showing how stable is the time transfer capability of the solution. We can also see here how when we replace the short distance links by long distance in the first two hops, in this case, using 25 kilometers cables, we obtain very similar performance. So here we tested with 25 kilometer cables, but the same happens with cable lengths up to 100 kilometers, which is the maximum distance supported by the usual SFPs that we can find in the market. We have generated some graphs, including the histogram of the time error for the first node. We can see the Gaussian distribution. Also the time error against observation time, where we can see the deterministic behavior of the solution. And we also included the Allen deviation just to show further information about the stability of the time signals. So in terms of frequency distribution performance, we can see in this figure the phase noise of all the White Rabbit nodes of the daisy chain. If we look at the results in the frequency offsets which are closer from the carrier, we can see, for example, that in all cases, the phase noise is below minus 90 dBc per hertz at 10 megahertz offset, meaning that the short-term stability in frequency is well preserved within the daisy chain. We have also included the Allen deviation just to give an idea about the long-term stability in frequency of the solution. So to summarize, we have discussed the multistatic radar and phase array antenna as two of the systems which are becoming more and more relevant as part of the evolution of the radar. So these type of systems provide many advantages for the radar performance, but also present new challenges in terms of synchronization requirements. So we have presented the solution based on resilient time servers and high accurate timing distribution based on White Rabbit, which can be implemented to meet the exigent requirements of these radar systems in terms of synchronization and also resiliency. So we provide some test results to show that it's feasible to distribute sub-nanosecond time and low phase noise clock signals in different network topologies for synchronizing the different elements of the radar system. We also presented the different options and form factors which are available within the solution ecosystem for integrating the synchronization capability in the radar equipment in the most efficient way. In relation to this, Orolia's team can provide the professional services and technical expertise in order to help with the design of the timing solution as well as with the commission and deployment of it. So that's all for today. Thanks everyone for your attention. And now I think it's time for the Q&A session.
All right, thank you, Carlos. We have one question come in ahead of the webinar. How scalable is this technology in terms of the number of nodes, higher speeds?
Yeah, that's very relevant. Actually, it's one of the main points, the main features that we can achieve thanks to the characteristics of the White Rabbit technology. So far, there is no limitation in the number of nodes. So we are talking about hundreds, even thousands of nodes can coexist in the same network. We have mentioned specifically the daisy chain topology. In this case, we have tested daisy chains up to 15 nodes, and we are able to still measure the sub-nanosecond accuracy in this scenario. But of course, then for the big deployments, we always recommend following a tree topology for increasing the robustness of the system. But yes, in general, there is no limitation in the number of nodes thanks to the characteristics of the protocol of the White Rabbit solution.
All right, and next, have you tested these in a wide area network? And if so, do you have any numbers or lab results from that?
Yes, absolutely. So there are actually some public results that it's possible to share, so we can follow up with this. So recently, we published some results related to a deployment of more than 1,000 kilometers, and we're able to measure in this scenario also the sub-nanosecond. So in this case, it was also interesting because it was a deployment using the usual telecom networks. So we'll just place some hubs for regenerating the time and using the proper sync key transponders and DWDM multiplexation. And we're able to deploy the link and measure very similar performance to what we can achieve in the local scenario. So it's very well escalated in terms of number of nodes and also long distances.
All right, and someone mentioned they didn't see a router in the network topology you presented. Do any of those devices have the functionality of routing the PTP packets throughout the network?
So this really depends on the type of deployment that you are considering. If it's something specifically for telecom networks, the approach can be different. In this case, normally the data goes along with in the same links, but there are always techniques. So for example, for integrating the data on the networks, we use DWDM multiplexing. So we dedicate only one G channel for the timing, and the rest, it can go with the data. but normally it's a good approach, like separating for preserving the best timing performance in the links. But yes, of course, it's possible to integrate, and it's something that we also study like on case-by-case basis, depending on the infrastructure and use case that we are dealing with.
All right. Someone asked, why use, what are the advantages to using WRZ16 instead of just a normal White Rabbit switch?
Yeah, so the White Rabbit Z16 is a product designed for the industrial applications within the critical infrastructure. So we have included there, we have redesigned the hardware to make it more robust, to meet the exigent requirements of the production networks for the industry. So we did it also, like thinking, for example, in the fintech applications that they have like very high requirements in terms not only about the system itself, but the monitoring tools that they need to use. You need to provide really tools for controlling the status of the device and the synchronization network at during all the time. Also for improving the interoperability with the different protocols. So for example, the White Rabbit Z16 can interoperate with the telecom profiles of PTP, of course with NTP. So it's a big variety of interoperability options. Also additional tools that we included also related to these industrial requirements, for example, the resiliency. So we are talking that the Z16 is capable of working, what we have mentioned also in the presentation, with multi-source time references. So you can receive in the distribution network references directly from a GNSS receiver through 1 PPS and 10 megahertz, or from an atomic clock, but also from PTP in the same network, from another White Rabbit link. So everything is coexistent in the same system, and we have smart algorithms there for providing the resiliency. So again, we are talking that when the primary reference fails, the system will be able to jump to the next time reference without impacting the performance. So this is all the types of requirements in industry that we are putting in the White Rabbit Z16, and which don't exist in the previous or the conventional White Rabbit switch, which was designed for scientific applications.
All right, thank you. Someone asked, how much training is needed for this? How turnkey is this system?
Yes, actually, it's pretty simple in the sense of the deployment. The devices will work plug and play. It's also one of the main advantages of the technology. So you don't need to place like a complex commissioning with calibration of the cables, of the delays of the system. It's very straightforward, so you can just deploy, especially locally. Of course, in a local scenario, you can just place the device, connect the optical fiber, and you will be able to measure the sub-nanosecond accuracy. So if in the case of long distance deployments in wide area networks, the case is a bit different. So for this, we provide the specific professional services for working on the best way to deploy the link, and considering if some kind of calibration will be required, we can also offer. But in general, the technology allows plug and play links for this level of performance.
All right. I've had a few questions about if the slides will be made available. Yes, we'll make those available in the post-show email that you receive. If you're interested in working together on a specific project, you can just click yes to the poll question, and we'll route you to the right account rep for your industry and your locale. Someone asked, what's the maximum physical distance across all nodes of a network?
Yeah, so there is not a limitation for the protocol itself. So when we talk about the maximum distance supported, so for example, in the presentation, I mentioned 100 kilometers. This is not a limitation, of course, of the protocol. It's just the power transmission of the SFPs, the transceivers that we are using. So if the transmission has enough like power for reaching the distance, the protocol can work with it. This is the case why normally for a point-to-point link, we talk about 100 kilometers, because this is what the SFPs, which are commercially available, support. But if we want to extend this distance, we can do it without any problem, just using, for example, as I mentioned before, Sync-key transponders, optical amplifiers, or of course additional White Rabbit nodes for regenerating the time. But there is no limitation in the length of the link, which is like related to the protocol. This is why we were able, for example, of deploying this more than 1,000 link connecting Chicago and New Jersey for a customer in the fintech market. So this is, I think, it's the longest White Rabbit link, which is right now like in production, but it's not a limit. So probably this distance, and hopefully it will be overcome like very soon.
Are there any, what limits the phase noise performance in your White Rabbit implementation? Is it the output XO?
Actually, no. It's not in our case for the White Rabbit technology, which uses the physical layer mechanism for recovering the clock from the network and disciplining the internal oscillator. It doesn't really depend on the oscillator that we are using. We don't need to put rubidium or very high performance local oscillator for achieving very good results in the phase noise. This is something which we do with additional hardware, additional expansion boards that we include in some of the devices, and this way we can improve the jitter of the solution and meet these requirements that we are discussing, and we presented the results also in the presentation.
And you mentioned a jitter of less than 50 PS in the system. Do you have a need to reduce it even less than 1 PS or lower? And if yes, at which time scale in your view?
Yes, so we mentioned the yes, there is even yes. So I think we are talking when I mentioned the jitter lower than 50 picoseconds. This is it was related to the timing signals. So basically, what we are saying is the standard deviation of the 1 PPS signals. So this is typically around 15 picoseconds in a point-to-point link. But if we think about a jitter as a requirement for the frequency signals, typically considering the integration in frequency of the phase noise, so this is typically the RMS jitter. In this case, with the low jitter devices, we obtain around 1 picosecond or even less than 1 picosecond of RMS jitter for one hop. So we are able to also meet this requirement with the solution.
All right. And do you have any plans to implement White Rabbit across wireless tech, or are the latencies too high for that?
This is something very interesting. It's an option we are exploring, and probably we don't have, of course, nothing like commercially available right now, but it's something which should be feasible. There are some proof of concept already placed there, and we really would like to go in this direction. So probably in the future, it's something that we will also see some progress in that direction.
And how robust is White Rabbit against temporary loss in fiber connectivity?
Yes, so this is why the requirements that we mentioned, yes, to make a robust solution. So we place different tools for avoiding the issues related to, yes, any kind of failure in the network. So here we are saying that the approach will be using different redundant links, for example, so if this provides actually redundancy in terms of the time references, but also network resiliency based on purely just the links, the optical fiber that we are considering. So if one link fail, the system is automatically able in the White Rabbit set family devices to jump to the next time reference available without impacting the performance. So this is the straightforward way that we have for providing these protections against failures in the network. And also the devices, the White Rabbit devices, incorporate. This is also one interesting feature of the White Rabbit set family, which includes the White Rabbit set 16, the possibility of integrating a whole overclock. So even if we lose all the external references in one node, in one White Rabbit node, we can jump into the whole overclock and ensure or minimize the time drift during this downtime period. We have already options on the whole over ensuring a time drift lower than 1.5 microseconds after 24 hours.
All right. And I don't know how deep you want to go on this, but how can you expand a little on the testing methodology to how did you test the sub nanosecond accuracy?
Yes, there are different ways. Normally, what we use is our 1 PPS outputs from the devices. So this is just you measure the 1 PPS directly with one oscilloscope or with one time interval counter. So you are comparing the 1 PPS, which is providing this reference directly from the internal oscillator of the device, and you are measure there perfectly. It doesn't lie. So you measure the level of accuracy directly. There is no software involved or anything. So this is the straightforward. This is how we normally do. But there are also, for example, in some applications in the fintech market, it's very typically to measure the accuracy of the system using time stamping. So basically, you are synchronizing using White Rabbit different time stamping devices, using, for example, the 1 PPS output from the White Rabbit devices. And then you do the time stamping in all the nodes which are synchronized, and you measure the error in the time stamping. So we have also some results this way that show that the time stamping, if you have a good time stamper there, you can measure sub-nanosecond accuracy in the time stamping. So in the same traffic, measuring the difference in the time stamping on each node, you can also see the sub-nanosecond accuracy there.
All right, excellent. That about does it for our questions. Great questions from this audience, by the way. We do a lot of these webinars, and we sometimes only get a handful, but this was a very, very good audience and a lot of good questions. So if you haven't voted in our polls yet, check out the polls tab on the right. You can choose to be contacted to see how White Rabbit might improve the accuracy of your radar application. And if you let us know what types of configurations you've got, we can come into that conversation a little more prepared. So I want to thank you, Carlos, for your time. At the end of this event, when we hit end, you'll be redirected to a white paper on our site that goes a little bit deeper on this topic. Any closing thoughts, Carlos?
Nothing. I think, as you said, it was very interesting round of Q&A. So just thank everyone for attending, for your time, and just see you next time. Thank you very much.
Thank you, everybody.